All right, let's dive right in. In this explainer, which is based on the fantastic work of Dr. Nima Mahadian, we're going to learn how to take raw, messy signals and turn them into clear, compelling stories. This is a super practical guide to nonparametric spectral analysis, or SPA, using MATLAB. Our goal here is to make every single concept simple, clear, and something you can use right away. Now, before we write even a single line of code, I want this idea to really sink in. This isn't just some catchy phrase, it is the absolute core philosophy that will guide everything we do. See, our goal isn't just to run a script, it's to conduct an investigation. The code is just our tool, but it's our understanding that's going to lead us to the truth. So how do we build that deep understanding? Well, the entire analysis, everything we're about to do, hinges on one incredibly powerful idea: comparison. You see, you can't understand data in a vacuum. You always need a reference point. To do this, we're basically going to operate in two parallel universes of data: the real world and an ideal one. Okay, so on the left, you've got the real world. This is our actual data. And yeah, it's messy. It's corrupted by something we call colored noise, which basically just means the noise isn't random. It has its own hidden structure. Then on the right, we have the ideal world. This is our perfect reference, our control group. Here, the signal is corrupted by pure white noise, which is perfectly random and has the same power at every single frequency. By constantly comparing our messy, real-world results to this clean, ideal world reference, we can start to uncover the truth hidden in our data. Now, just like a detective arriving at a crime scene, the very first thing we have to do is secure the area. We need to make sure our analytical space is clean and free of any contaminants that could lead us to the wrong conclusion. This whole section is about setting the stage properly so that the evidence we collect is pure. You might look at these first few lines of code, clear CLC, clear all, close all, and think, okay, yeah, basic housekeeping. But the philosophy behind them is so much deeper. See, spectral analysis is all about statistical averaging. If you have old variables or plots just hanging around from a previous run, they can seriously contaminate your judgment and totally invalidate your results. So the point is this: a clean slate isn't just good practice. It's an absolutely non-negotiable requirement for good science. Our next prep step is just as critical. We've got to remove trends. Look at that before signal. See how it's kind of riding on a slight upward slope? That's a trend. And here's the problem: all spectral analysis techniques assume your signal's average is zero. A trend like this pumps a massive amount of artificial energy into your signal, especially at low frequencies. It's like a smokescreen that hides what the system is actually doing. So we use the detrend function to get rid of this false evidence. That way, we know the energy we analyze later is from the system itself, not some hidden bias. Okay, so our data is prepped, it's clean, and we're ready for the main event: identifying the system. We have an input signal, we have an output signal. What we want to know is, what's the black box in between? What transforms the input into the output? Our key tool for this investigation is a MATLAB function called CPSD, which stands for cross-power spectral density. And this right here, this is where the magic of statistics really shines. The system's behavior, its transfer function G, can be found just by dividing the cross-spectrum of the input and output by the power spectrum of the input. I mean, think about that for a second. We don't need some complex physical model. We don't need to solve any crazy differential equations. With basically one line of code, we can calculate the system's behavior directly from the statistical properties of the signals we measured. It's incredible. So, we've got an answer. We've identified the system. Awesome. But in any good investigation, getting an answer is just the beginning. The next, and honestly the most important question we have to ask is, can we actually trust this answer? Is our finding robust, or is it just some random fluke based on the settings we chose? We have to interrogate our own result. To check for reliability, we do what's called a robustness check. The CPSD function uses a parameter called a window. You can think of it like changing the lens on a camera. Different lenses give you different perspectives. So by running our analysis with different windows, we're basically looking at our finding from multiple angles. If the result changes wildly every time, like you see on the left, that's a huge red flag. It's unstable. But if the results stay pretty much the same, tracking each other closely like on the right, then we can be confident our finding is robust. And here is the result from our data. The two curves, each one calculated with a different analysis window, are tracking each other super closely across the entire frequency range. This is beautiful. This is exactly what we wanted to see. This outcome confirms that our identification of the system is solid. We can now move forward feeling really good that the system G we've calculated is a trustworthy picture of what's really going on. Now, identifying the system is a huge step, but it's only half the battle. Some of the most valuable insights actually come from analyzing what's left over. It's time to investigate the noise. If the system is the main character in our story, then the noise is the sneaky accomplice that influences the final outcome, and it's time to unmask it. The basic idea here is actually really simple. The total energy we see in the output signal is made up of two distinct parts. First, there's the energy that comes from the input signal, passing through the system we just identified. And second, there's all this leftover energy, the noise power. This is the part of the output that our system model can't explain. Our mission now is to isolate that second part, the spectrum of the noise itself. The logic for isolating the noise is pretty straightforward. It's basically just subtraction. Step 1, we measure the total power spectrum of our output signal. Easy enough. Step 2, we calculate the power that we know comes from our identified system G. And step 3, we just subtract that known system power from the total output power. Whatever is left over, by definition, has to be the power spectrum of the noise. But once we have the noise, how do we interpret it? Is it a lot? Does it have a structure? To answer that, we need our benchmark again. We need to go back to our ideal world data. We do the exact same noise calculation, but this time on the data set where we know for a fact the noise is perfectly white. And the result, as you'd expect, is a perfectly flat line. This tells us the noise power is constant across all frequencies. This flat line is now our perfect reference, our baseline for judging the true nature of the noise in our real system. And this brings us to the final reveal, the moment of truth. We have the noise signature from our real-world system, and we have the perfect white noise reference from our ideal system. Now we're going to put them side by side. It's time to compare them directly and finally see the true color of the noise that's been messing with our data all along. So, take a look at this final plot. That flat blue line, that's our white noise reference. Exactly what we expected. But look at the yellow line, the noise from our real-world data. It is clearly not flat. It has way more energy at low frequencies than it does at high frequencies. This is the smoking gun. This is the very definition of colored noise, and it has a massive implication. It means the standard analysis is being systematically biased by this hidden structure. We've now not only identified the system, but we've also fully characterized its primary contaminant. So, what should you take away from all of this? It really boils down to three crucial points. First, your analysis is only as good as your data. The quality of your data directly dictates how reliable your results will be. Second, the analysis is sensitive to parameters. Your choice of a window isn't random. It's a tool you have to use to test how robust your findings are. And third, the analysis is shaped by the color of noise. If you don't realize your noise is colored, your results are going to be biased, period. This whole journey shows that spectral analysis isn't just a formula you plug things into, it's a statistical investigation. And this brings us full circle, right back to where we started. We can now feel the full weight of this statement. We've seen firsthand how understanding trends, checking for robustness, and characterizing noise are the things that lead to real insight. The MATLAB code? That was just the tool that let us conduct our investigation. But the true insight, the story hidden deep inside the signal, that only comes from a deep understanding of the full picture. The data, the system, and its ever-present accomplice, the noise.